This is the strongest material in the universe, or rather a plastic facsimile of it. It has to be. You see, if I were to go where this stuff is actually found, I'd be immediately flattened into an atom-high thick paste. And if I was actually holding this in my hand right now, it would immediately explode and destroy the continent that I'm on. What is nuclear pasta? And just how strong is it?
Now entering the facility.
Dear viewer, what makes a material strong? Why is it so much easier to break your toe than it is that blasted coffee table? Well, the ultimate strength of a material ultimately comes down to the interior structure of that material, its atoms, molecules, and how they all fit together. So, for example, a material like chalk is relatively weak because it's full of holes and tiny skeletons, and the material itself isn't really well organized. Diamond, on the other hand, is extremely strong because it's relatively well organized with few defects. The strength of a material is that material's ability to resist stress without straining or changing shape. Now remember those terms, we'll come back to them in a little bit. For now, it's time to go to space. Arya, ready the ship!
Will you bring me back some pasta?
You know I will.
Mamma mia!
As a sufficiently massive object like that star in the background or your mama furiously burns through fusion fuel from hydrogen all the way up through heavy elements, it is resisting gravitational collapse through the energy that is being produced by that fusion. But as a star starts to burn iron, that's when it starts to die, because it actually takes more energy to fuse iron than it releases.
Also like yo mama.
I don't think that one worked. A large star may live for millions of years, but it only takes less than a second for one to die. With a core creating iron in a reaction that doesn't sufficiently push back against gravity, in about the same time it takes you to blink, gravity collapse is crashing towards the core. If the star is heavy enough, the collapse crushes past electrons' refusal to occupy the same space, or electron degeneracy pressure, and forces them to combine with protons, creating neutrons. If the star is huge, collapse will smash past this next limit, neutron degeneracy pressure, and create a black hole. But then, we don't get any nuclear pasta. The collapse in our case, stopped by neutrons, then rebounds off the compressed core with a shockwave that annihilates the iron and heads back out towards the universe. A few hours later, remember, stars are huge. The shockwave reaches the star's surface and explodes in the universe's greatest fireworks show, a supernova. This both violently generates all the heavy elements that populate the universe and leaves behind a near-perfect sphere of degenerate matter. A neutron star is born. Neutron stars are the most extreme objects in the universe that are still objects. We're talking about magnetic fields strong enough to rip you apart atom by atom from 1,000 kilometers away. We're talking about surface gravity so high that if you tried to stand on a neutron star, you would be immediately squished into an atom-high thick paste. We are talking about something that, during gravitational collapse, goes from 10 septidecillion different nuclei in a fraction of a second to one. A neutron star is like a single nucleus, but it's a star, and it's therefore as dense as nuclear material itself, another gigantic number we can't even begin to comprehend. Now, if nuclear star stuff is starting to sound pretty strong, as we defined it, you're right. It is. And that brings us back to the pasta.
Mamma mia!
Today's video is sponsored by Surfshark. I'm award-winning science educator and Tom Cruise if you left him on a desert island for a while, Kyle Hill. For my day job here at the facility, I research a lot of weird stuff. How to bring tarantulas back from the dead, genetic codes of zombie viruses. I need a real shark behind me while I surf. The sponsor of today's episode, Surfshark. Surfshark is a premium virtual private network service that encrypts all of your information sent between your devices and the internet. You can use Surfshark to bypass censorship, mask your IP address, change your device's virtual location to access YouTube in Nigeria. Surfshark does not monitor, track, or store what you do online. That means no connection or activity logs. And unlike other premium VPNs, Surfshark now has thousands of servers in over 100 countries. Be secure on the majority of the Earth's surface. Use the offer code KYLE for 85% off from now until the end of the year and 3 extra months
free, you're welcome. There's a money-back guarantee, and you get an unlimited number of devices on just one account. While you're surfing, protect your turf. Surfshark. In 2018, scientists published a paper entitled The Elasticity of Nuclear Pasta. In it, they used simulations to probe the interior structure of neutron star stuff. And what they found was that under the most extreme conditions you can find in the universe, neutrons didn't look like neutrons anymore. They didn't look like the little spheres you learned about in school. No, they took on exotic shapes like sheets and cylinders that looked a little tasty.
The paper details lasagna-like sheets of squished neutrons in configurations no one had ever seen before. And they weren't just limited to one dish.
Mamma mia!
There was nuclear gnocchi, anti-gnocchi, waffles, and spaghetti. And thanks to the scientists making their work available to anyone as a 3D model, you can investigate these shapes with your own two hands. Using my Pulse XE 3D printer that I got from Matter Hackers, link in the description, I translated the pasta into something that I could print, applied a few coats of shiny science paint, and brought the interior of a dead star to life. It really is amazing. The work of scientists on the most extreme things known to humans translated into models, transformed into something anyone can render and see for themselves. It's the best kind of science.
So, just how strong are these tasty structures? Well, now's the time when we're going to return to that stress versus strain curve that I mentioned earlier. So I'm going to draw you two axes. The y-axis here is going to be stress or force or pressure on a material, and the x-axis, is going to be strain, how much that material deforms. Could be an inch, a millimeter, a meter, doesn't matter. What matters is that for something like steel, the graph looks kinda like this, where this linear slope here at the beginning part of the curve, the slope, rise over run, stress over strain, is equal to the shear modulus. How much a material can resist deformation depending on the stress, strength as we defined it. So if this is the curve for steel, I'm gonna now, for a comparison, draw the curve for nuclear pasta. And let's just say, I don't know, for every second that we are drawing this line on your screen, as I'm about to do, nuclear pasta gets
10 quadrillion,
times stronger than steel.
10 quadrillion.
Times every second that I'm drawing this line. Okay? Here we go. Every second,
10 quadrillion.
times stronger. Every single second. Every second.
10 quadrillion.
Just a couple
10 quadrillion.
times more times, please. Okay. And stop. This is where the strength of nuclear pasta lies. Because of its composition, because of its extreme of extremes, it is a billion times stronger than steel. The strongest material in the universe, and it's not even close. Now, I know these numbers are literally impossible to conceptualize, so how about this as an example? I could hit some nuclear pasta stuff with a hammer that weighed as much as Earth, and nothing would happen to it. Not a scratch. I did the math. That means nuclear pasta could easily withstand the might of Mjolnir, one of the strongest weapons in fiction. But Mjolnir is canonically made out of the heart of a dead star. A neutron star? That means, yes, dear viewer, that if any Marvel scientist was to look at the nanoscopic structure of this hammer, what would they find? Nuclear pasta. That's how strong this stuff is. And that's canon now. You're welcome, Hollywood. Until next time.
Now exiting the facility.
Thank you so much to the very nerdy staff at the facility for the direct and substantial support in the creation of this here video. If you want to join me here at the facility, drape on a silky white lab coat, get videos early, join our private Discord, get private members only monthly streams with me, go Go to patreon.com/KyleHill and join the facility today. And hey, if you support us just enough, you get your name on Aria here each and every week. What glory it is to be. And, I mean, there's hundreds of you. What am I gonna do? Like, I'm trying to fill time or something. So you can't really hold nuclear pasta as I was holding it in this video. I was just holding a representation of what it's like inside of neutron star crust. Yes, it's a star with crust. It's a ravioli, maybe. But that stuff is at extreme temperature and pressure. If I removed it from that pressure, then gravity would no longer be keeping all that material that's in a tiny space together in that tiny space. And if I removed it from that environment, it would immediately explode outwards and destroy everything. And that's why if you broke Thor's hammer, it would also destroy the continent that they were on. Thank you for coming to my TED Talk. Thanks for watching. Yes, that is how I sound.